All right, Donkey Kong. This is just a quick little summary. Ions, naming ionic compounds, and writing formulas for ionic compounds. All right, so looking at your periodic table here, we got to understand that the compounds that form through the transfer of electrons, the ionic compounds, they're always going to be involving your metals, which they could be this column, anything transitioning through to here. And then, so these are all basically metals. And then non-metals are going to be this corner up here. So an ionic compound generally is going to involve a metal with a non-metal. So for example, lithium oxide, iron 1 oxide, calcium fluoride, strontium bromide, potassium nitride. You're always working with a metal and a non-metal, okay? Now I'm not really bringing up polyatomics here, but that's just the gist of monatomic ions and the compounds that would form. So the basic way you want to read this table and the way it's kind of lined up is, we're talking this column here has 1 valence electron. This column has 2 valence electrons. The transition metals are variable, so they can have 1, 2, 3, or even 4 valence electrons. They call that multiple ionization states. It just really depends on the specific metal. And then we have 3 valence, 4 valence, generally not going to be involved in forming ionic compounds. 5 valence, 6 valence, 7 valence, and these have a full valence shell, okay? So 1 valence, 2 valence, 3, 4, 5, 6, 7, full. Now what that means is that, like on this column here, that 1 valence electron is readily lost when it gets together with a non-metal who would, certainly doesn't mind getting that valence electron. So for example, oxygen has 6 valence, so it would like to get 2 more. And so if we would put sodium with oxygen, sodium would have to give up, you'd have to have 2 atoms of sodium, each give up 1 electron, and then the oxygen would have to gain both of those. I'll show you an example of what I'm talking about there. It's a little bit unclear, but so anyways, 1 valence, 2 valence, 3, 4, 5, 6, 7 full. And then what kind of charge would form then? Well, if this is 1 valence, it tends to lose that valence, so +1, +2, +3. Doesn't really form a charge. Okay, now these guys here, okay, -3, -2, -1. So why did I go negative? Well, it's easier to gain 3 than to lose 5. So 5 valence, gain 3, become -3. 6 valence, gain 2, -2. 7 valence, gain 1, becomes negative, okay? So you kind of have to have that pattern, or that, just the layout of the table kind of pretty well understood. So let's take a look at a couple examples here. How would we start to put these things together? Well, let's say we had lithium. Lithium forms a plus ion. And if you want to come over here and join lithium up with, say, oxygen, okay, oxygen forms a 2- charge. So what we could do here, we could do a crisscross technique where we say, hey, look, the charge of the anion here, the oxygen, this charge becomes the number of cations. So Li, this 2, comes down here, and then there's an implied 1 there that's going to come down to the oxygen. And so we call that lithium oxide. Okay, changing, that's our "ide" ending there. If we had something like, let's say we had magnesium with oxygen. Magnesium forms a 2+. Oxygen is going to be a 2-. In this case here, we're going to have Mg. This 2 is going to come down to the magnesium. This 2 is going to come down to the oxygen. And then we basically have a 2-to-2 ratio, which is a 1-to-1. So you would rewrite that. That's going to be magnesium oxide, MgO. So magnesium oxide. And we could do several examples here. We could say, what about potassium? Potassium's a plus ion, and let's say potassium gets together with chlorine. Chlorine's a negative ion, so we're basically going to flop these. There's a 1 here and a 1 here implied. So K Cl1, but we don't leave those ones there. That's a little redundant, so you just say KCl, and we're dealing with a compound, or not a compound, we're an ionic solid here, potassium, let's see, chloride. So again, we're changing that ending to IDE. So let's do maybe one more. Let's say we had, let's say we had calcium. Calcium forms a 2+, and we want to join calcium with a phosphorus here. So we go, okay, what's phosphorus's charge? Well, phosphorus is in that 5 valence, so it gains 3. So we'd have Ca, calcium, and then the 2 is going to come down here, and we would call that calcium phosphide. Again, that ending IDE is in place there. So that's just a basic idea on the monatomic ions. You also have to deal with polyatomics. So a polyatomic ion is basically where you have more than one type of ion and the entire thing is charged. So for example, you got phosphates, or you got hydroxide, or nitrates. There's a couple examples there, and these will all even have positive ones like ammonium, NH4, it's a positive charge, the whole thing is charged. So it's kind of weird. The atoms of the polyatomic are actually held together covalently, but the entire thing is charged, and then it can join up with another ion. So for example, you could say, all right, let's see lithium plus and phosphate, PO4, 3 minus, right? We do our crisscross technique here. Lithium, the 3 is going to come down here, so that'd be 3 lithiums for every 1 single phosphate. Okay. And you also should be familiar with what if we did calcium with phosphate? We'd say, okay, calcium's a 2+, phosphate is a 3 minus. All right, crisscross. Ca3, then the 2, PO4. But we have to put this in parentheses because we want 2 of the entire thing in parentheses. Sort of have to distribute that out in a way. So there's a couple examples of polyatomics. And the other thing I might mention here is when you're dealing with these, the transition metals, for example, if we got like iron forms, like I said earlier, either maybe a plus or a +2 charge, depending on which, kind of how he's dealing with the other negatively charged atom, the anion. So you could have iron with oxygen would look like this. We'd have Fe, the 2 comes down here, O, and then because of those multiple ionization states, we have to call that iron. We have to have a Roman numeral to signify which iron we're dealing with. So we go back and we look at the charge, that's iron 1, so iron 1 oxide. Iron 2 oxide, we have Fe2 plus O2 minus, Fe, bring the 2, O2, but then that's a 1-to-1 ratio, so you'd say FeO, and then in naming that, we would say iron 2 oxide. So in a nutshell, that's a little bit of ions and naming and formulas. Hope it helps.